Hello everyone. So again, welcome back to our latest lecture session. So let's have a quick recap of what we have been up to in the last lecture session. So we have been looking at or trying to look at, let's say, understanding the system holistically, right? So in that context, we started looking at one particular example as in reductive dechlorination of this perchloro or tetrachloroethylene by Fe2 plus, right? So in that context, to see if that's feasible or not feasible, we looked at one particular scenario wherein we assumed that all the activities were equal to, I guess, 10 power minus 3, but that the pH was at 7, right? So in that context, we went ahead and calculated the relevant PE values. And from our background, we know that, let's say, if PE of a particular half reaction is greater than the PE of another half reaction, right? The PE or the half reaction with the greater PE, right, would go through as reduction, and the other half reaction would need to proceed as oxidation, right? So that's something that we understood or derived to, I guess, right? So we looked at the equation as in, we had this particular equation as in PE1 minus PE2 is equal to 1 by N1 N2 log K by Q, right? So we had this particular equation, and we also looked at a particular graph, let's say, right, or a figure where we tried to understand that, let's say, the case that for PE1 and PE2 to approach each other or for the system to reach equilibrium, right, we saw that when PE1 greater than PE2, for the system to approach equilibrium, we saw that PE1 needs to go through as reduction and PE2 needs to go through as oxidation, and that's something again we can understand from this particular equation that we have just written down, right, wherein PE1 minus PE2 equal to 1 by N1 N2 log K by Q, right. So only when it is positive, as in the left hand side is positive when PE1 is greater than PE2, we know that K is what now, greater than Q or Q less than K, meaning the reaction would go from left to the right or proceed from the left to the right. And the way we have written down that overall reaction was when 1 went through as reduction and 2 went through as oxidation, right. So again, understand the particular system both in terms of the relevant aspects and also the relevant math, I guess, right. So again, let's go back to our example here. So the first case we considered was there were no other reactions, right, no other reactions other than redox, yes, and I believe we calculated the PE value for this half reaction, and the second one too, PE1 came out to be 13.03 and PE2 came out to be 8.84. Obviously, the case was that we assumed that all the activities were equal to 10 power minus 3 and that the system was at pH is equal to 7, right. And obviously, the major aspect or assumption for this particular scenario was that we assumed that there are no other reactions. And from this we see here that PE1, right, PE1 which is for this half reaction is greater than PE2, right. So what does that mean? That PE1 or the first half reaction, pardon me, is going to proceed as reduction, or Fe3 plus is going to be reduced to Fe2 plus, right. And because PE2 is less than PE1, right, we are going to have to swap that particular half reaction as in C2HCl3 plus Cl minus would have to proceed as being oxidized to C2Cl4 plus H plus 2 electrons, right. So this is how the system should proceed if there were no other reactions, and that is because PE1, right, was greater than PE2, right. What does this mean? That C2HCl3 is going to reduce Fe3 plus or ferric iron to ferrous, but again this is something that is at odds with what you would observe out there. So we are trying to understand, or we are going to try to understand why this is the case, right. So again, we are going to look at the other scenarios obviously, but before we go further, obviously we want to be familiar with how to be able to use Vimintek in such scenarios to be able to estimate the PE. So let's go ahead and have a look at that for this particular scenario, right. Or I guess, okay, the Vimintek will always consider complexes, so that's going to be difficult, I guess, right. Anyway, so we have to skip Vimintek here because it can't take this hypothetical scenario when we exclude the complexes anyway. So we are going to go through and look at the other scenario that we have for today. So here we are going to consider, other than redox, we also have complex formation, right. So we are also going to consider the case when complexes are formed, and the same reactions as in Fe3 plus electron goes to Fe2 plus. We are going to start with that, right? And also we have the relevant other half reaction C2Cl4 plus H plus 2 electrons goes to C2HCl3 plus Cl minus, right? And we have the P naught values to be 13.03 I believe, and P naught to be 10.84, right? And obviously here with respect to complex formation, right, it has no effect on either C2Cl4 or C2HCl3 or the relevant other what do we say compounds here in this half reaction. So the P which was 8.84, right, from the earlier case is still going to be the same case here, right? And so we are going to skip having to recalculate the PE for this particular half reaction when we consider complex formation. But obviously with respect to half reaction 1, you know that Fe3 plus can or will form complexes, right, and Fe2 plus not to a great extent, but you do know that Fe2 plus 2 will or can form a few complexes, right. So here we are going to shift from the theoretical or the hypothetical scenario where we assume that only redox reactions go through and no other reactions go through, and shift towards the realistic scenario, and this will help in understanding, let's say, how, let's say, the relevant other chemical processes we have discussed thus far are relatively important and how they fit into the bigger picture, right. So let's look at that now. So obviously we are midway, we are now considering that we also have complex formations, and this is something obviously we know, right. The metals Fe2 plus and Fe3 plus, they are electron poor compounds, right. So they attract the electron rich compounds, the ligands, yes, and they can form these coordinative relationships or have the aqueous complex being formed, right. So you know that. So obviously let's say for a total Fe of let's say 10 power minus 3, right, that is what we assumed in our previous examples, right. Fe3 plus was 10 power minus 3 and Fe2 plus was 10 power minus 3. But you know that if you put in a total, what do we say, Fe3 or 10 power minus 3 concentration, the actual concentration of the free metal Fe3 plus is going to be much lower. Why is that? Because most of the metal is going to stay as complex and not exist as, what do we say, the free metal, right. So obviously this will lead to a change in your particular what do we say, variables in this equation, right. P equal to P naught minus 1 by n, which is 1 electron transfer here, log activity of Fe2 plus, right, by Fe3 plus, right. So this is the equation for which we are going to try to recalculate the relevant what do we say numbers, considering that we have complexes being formed, right. And we now know that Fe2 plus and Fe3 plus concentrations are not going to be the same as this Fe2 plus total, which was 10 power minus 3, and Fe3 plus total, which is also 10 power minus 3. We know that Fe2 plus free metal and Fe3 plus free metal concentrations, right, are going to be lower than the total Fe2 plus and total Fe3 plus that is present in the, or that you are putting into the system, let's say, right, or you have in the system, let's say. So let's try to work this out first by hand and then by Vmintek, right, again to refresh our memory and also to be able to understand the system holistically. So let's say for the case of Fe3 plus, we are going to work this out, let's say, rather than working it out for everything, but we'll write down the tableau, right. So let's say what do I need to come up with? I need to come up with all my species. So the species here are going to be obviously H plus, OH minus, right, and then the free metals Fe2 plus and Fe3 plus. So for ease of calculation, right, and digging into the relevant background that we have had when we looked at the relevant aqueous complexes based aspects, right, we know that Fe2 plus will form complexes but not to a great degree. So at least for working out by hand, working out the system by hand, I am going to consider that Fe2 plus does not form any complexes, and most of the, or let's say all the Fe total for 2 plus stays as Fe2 plus itself. This is not a bad assumption, as we are going to look at with respect to Vmintek later on, I guess. But with respect to Fe3 plus, you know that most of the Fe3 plus, let's say, would stay as would form complexes, right, and very little Fe3 plus would stay as the free metal Fe3 plus itself, right. So let's try to just work it out with respect to Fe3 plus, assuming that little to no complexes are formed by Fe2 plus. So Fe3 plus, I guess, right, we need to look at the relevant complexes. So FeOH, right, 2 plus, FeOH twice plus, FeOH thrice neutral charge, right, this is still a complex, aqueous complex, FeOH for negative charge, right. So I guess these are the relevant complexes that I am going to consider, right. So how do I go about it now? I am going to, let us say, choose that H plus and Fe2 plus and Fe3 plus are my components, right, and these are my species, right. So if I write down the tableau, right, only with respect to Fe3 plus, let us say Fe3 plus, and what are the relevant what do we say, species that are relevant here. So let us say I am going to have to write Fe3 plus here and the 4 complexes FeOH2 plus, FeOH twice plus, FeOH thrice plus, right, and FeOH4 minus. So Fe3 plus 1, 1, 1, 1 and 1 here, the contribution. So obviously we are at this stage, I guess, relatively comfortable enough, or should be comfortable enough to be able to write the relevant tableaus or get the relevant tableau with respect to the relevant components without having to write the formation equations, right. So that is what we are doing here. So if you are not yet comfortable, I would guess, obviously I would suggest writing down the formation equations. So here we are going again with respect to the assumption that Fe2 plus forms little to no complexes, and I am just trying to understand the system with respect to Fe3 plus so that I can help visualize it better. So that is what we have here. So here if I do the component balance, right, what is that going to be equal to? Fe3 plus total is going to be obviously equal to Fe3 plus, right, or concentration of Fe3 plus concentration of FeOH2 plus, right, and that is obviously from this particular tableau and the relevant component balance, and FeOH twice plus FeOH thrice neutral charge plus FeOH4 negative charge, right. So obviously I need to be able to transform this particular equations into variables that I can what do we say, use or solve for, right. So I can express this in terms of the beta values again, plus Fe3 plus into what now, how do I write the relevant equations here. So obviously again we need to look at the relevant what do we say, complex formation equations. So obviously I believe we looked at beta star values, right, wherein we look at one step and the protonated ligand. Let us just have a look with respect to one complex formation. So let us say I am trying to form, let us choose one of, let us say this thing, FeOH twice plus charge, right. So here obviously I am trying to have the protonated form of the ligand, right, H2O, right, and obviously because it has to be direct, right, it has to be 2 here, and so I am assuming it is going to be 2H plus here. So hopefully it is balanced out, 2OH, and here it is 4, okay. So that is balanced out, and we know that the relevant coefficient is given by beta 2 star, I guess, right, and that obviously is equal to the concentration of FeOH twice plus H plus square by concentration of Fe3 plus, right. So obviously FeOH twice plus concentration is equal to beta 2 star, right, into Fe3 plus by H plus square, right. Similarly I can get the relevant equations for the other complexes, right. So obviously here I am just trying to refresh your memory and obviously get your neurons flowing, I guess, right. So here we again let me just try to write down this equation here, right, in the form of what we want here. So it is obviously going to be equal to Fe total or Fe3 plus total is going to be equal to Fe3 plus times 1 plus, and here it is going to be for the first complex beta 1 star by H plus, right, plus beta 2 star by H plus square, right, which is for this particular complex, right, and for the other two complexes too we can write it down similarly, beta 3 star by H plus cube plus beta 4 star by H plus to the power of 4, right. So obviously we now have the relevant equation in terms of two unknowns Fe3 plus and H plus, and obviously the relevant constants beta 1 star to beta 4 star, I guess, right. And obviously if you do the balance on H total, right, similarly you can then what do we say, solve for two equations and two unknowns and get the relevant answer by hand, right. Obviously we are not going to go through that, but let's use Vmintech to find out what these concentrations or actual concentrations of Fe3 plus and Fe2 plus are, right. So let's go back to Vmintech here. So I'm going to plug in Fe3 plus, right, and where is that here, Fe3 plus, and let's say I'm going to go with millimolar. So we went with 10 power minus 3 concentration, so we are going to try to continue with that, right. So it's going to be equal to 1 millimolar, add to the list, and the other case is Fe2 plus, also 1 millimolar, right. So I'm going to add that to the list, but again keep in mind that here we are having total component balances, right, or we are giving the system the initial total component, right. So obviously if you are giving Fe2 plus and Fe3 plus, right, you cannot provide Fe2 plus and 3 plus independently, right, the ions to the solution. So in general for the charge balance too, I guess, let's assume that we provided FeCl2 or such, or FeCl3, pardon me, FeCl3 as source of Fe3 plus, and let's say ferrous sulfate as source of what is it now, the ferrous iron, I guess. And let's go ahead, let me see what we had there, and we had back to main menu, right. Okay. So again what I am saying is obviously, so we are trying to work it out by Vmintech, right, Vmintech, and we need to give the total component balance, total component concentration. So Fe3 plus total we say is 10 power minus 3, and same case Fe2 plus total is 10 power minus 3, but for the relevant charge balance, let's say we are going to assume that we are having FeCl3, right, and FeSO4, let's say, right, and this obviously is source for the Fe3 plus and this for Fe2 plus, I guess, right. And for that obviously I need to put in Cl total is equal to 3 times 10 power minus 3, right, 3 times 10 power minus 3, right, and SO4 total is also going to be equal to the same molar concentration, which is 10 power minus 3, right. So if I am having FeCl3 naught at 10 power minus 3 and FeSO4 naught at 10 power minus 3, right, these are the relevant components, right. And let me plug in the relevant Cl and SO4, I guess, right. So Cl, where is Cl here? Cl is 3 millimolar, right, that is what we have seen, 3 millimolar, add to the list, and then SO4, I am looking for SO4 2 minus, okay, there it is, and here we have 1 millimolar again, right. So let's look at the edit list. So FeCl3 and FeSO4, right. So we are fine there, and now I am going to run it, let's say, but because obviously the pH is fixed at 7, I need to specify that the pH is fixed at 7, right. So that was the initial assumption, if you remember. So I am going to run the Mintech, right, and let's see what the actual concentrations of Fe3 plus and Fe2 plus are, and then plug them in. So Fe2 plus is 8.9 into 10 power minus 4, right. So I see that Fe2 plus concentration is slightly lower, but still similar to 10 power minus 3, 8.9 into 10 power minus 4, right. And let's see what the actual concentration of Fe3 plus is, right. And where is that here? That, as you see, is much lower, 1.1 into 10 power minus 11. So 1.1 into 10 power minus 11, right. So there you have it. So this obviously is the case for when pH is equal to 7 and the activities of the relevant total metals are equal to 10 power minus 3. So now after plugging in the relevant components into Vmintech, we saw that the actual free metal concentration of this Fe3 plus, right, is much lower, right, and that's by order of magnitude of what, 8 times. Earlier it was 10 power minus 3, now it's 10 power minus 11, right? So order of magnitude difference of around 8, right, which is a huge difference obviously. So obviously let's come back to our equation with this particular values. So we have Fe2 plus concentration equal to 8.9 into 10 power minus 4, and as you see that's still more or less similar to what we had initially, the 10 power minus 3 concentration, and Fe3 plus though is now equal to 1.1 into 10 power minus 11, right? And again that as you see is much lower, right, than 10 power minus 3, which was your initial total metal concentration, right. So obviously when we try to plug in the relevant values into our equation, which was P equal to P naught minus 1 by n log Fe2 plus by Fe3 plus, right. So what would you observe here? Obviously you see that Fe2 plus is more or less the same, right, but Fe3 plus is much lower, right. So here I guess we are increasing the value of this particular variable here, meaning the P value will decrease, I guess, right. So I can plug this in into Excel, let's say, and calculate that, or obviously again let's see how to get this done in Vmintech, I guess, right. So I'm going to go back to Vmintech, so fixed at 7. So here I need to specify the redox couple, right. So we have looked at how to solve it by hand. Obviously I need to plug that in and get the relevant P value, but I can also use Vmintech to be able to get that. So obviously for that I need to specify what are the relevant redox couples. Here obviously the system is with respect to the redox couple is Fe2 plus and or the redox couple is with respect to Fe2 plus and 3 plus. So that's what I'm going to have here. So I'm going to ask the system to limit to those couples based on the components that I have. So it's obviously only going to be Fe2 plus and Fe3 plus, and I'm going to add that to the list. And here you say that Visual Mintech will assume a fixed P value of 8, which doesn't make much sense to me. So obviously I need to go to the specify PE and EH menu. Okay, we are going to do that. Back to main menu. So here I guess parameters and specify PE and EH, and it's not fixed PE, right. I'm trying to calculate the PE, so it's not fixed EH. Again we'll come back to that. So PE or EH computed by supplying a guess for PE. So guess for PE I'll give it to be what it was earlier. I think it was around 13, so it should be lower. Let me go with 10, right, and it's not switch key, and let's say I'm going to supply a guess of around 9. Let's say we know that the PE value is going to be lower compared to its value that we had earlier, which was I believe 13.03, right. So let's go with that and save and back to main menu, and now run the Mintech, right. And now let me look at what the P value is. Okay, it's right here, and you see now that the P value is much lower. It's 4.9, right. And keep in mind that earlier we had a value of P value of 13.03, and now we have a value of 4.9, and let's try to see how this changes our particular system, I guess, right. So now the P did drop. So earlier case the P was 13.03, now it was, or it is 4.9, right. So let's try to understand what this means to us, I guess, right. So again keep in mind that we are looking at two half reactions, Fe3 plus electrons. One electron goes to Fe2 plus or is reduced to Fe2 plus, and we had C2Cl4, right, plus H plus 2 electrons obviously, right, and C2HCl3 plus Cl minus, right. And when we considered no other reactions, right, and we had a value of P for this particular half reaction was 13.03, and for this it was I believe Pe2 was 8.84, right, and because Pe1 was greater than Pe2, right, what does that mean? It means that 1 will go through as reduction, while 2 or this half reaction will be the oxidation one, right. But now in our case when we have complexes form 2 or complex formation, what did we observe now? We observed that the P1 now is now 4.9, right, while the P2 is still going to be equal to 8.84, right. The complexes do not affect these particular compounds here. And now what do we see here? We see that P2 is greater than P1, right. So what does that mean now? So 2 would go through as reduction, 2 would go through as reduction, right, while 1 would go through as oxidation, right. And again, what does that mean? That more or less means obviously that Fe2 plus is going to reduce C2Cl4 to C2HCl3, right. So, obviously, here you see that Fe2 plus is actually going to or try to reduce C2Cl4 to C2HCl3, right, C2HCl3. Again, so again why this change? Earlier we had what do we say, Pe1 to be greater than Pe2, but here we have Pe1 less than Pe2, and obviously again the whole point of it is that, or the basis for this is that here we are considering what do we see, a more natural case, which is also the formation of the aqueous complexes, right, which we did not in the earlier case. But here we see that Fe3 plus concentration is going to be much lower than the total Fe3 plus, right. And why is that? Because we have Fe3 plus existing in various complexes. Let us look at that for a second again, back to input menu or view output files, pardon me, and view species distribution. So, as you see, Fe2 plus 89% of the total Fe2 plus stays as Fe2 plus, but with respect to Fe3 plus, I guess they do not even list Fe3 plus here because it is at such low concentrations. 99.3% exists as complexes, or more than 99.9% exists as complexes, and little or very little or negligible amount what do we say, of the total Fe3 plus exists as Fe3 plus or the free metal. So, thus when you plug in the relevant values in your PE equation, right, for the reduction of Fe3 plus to Fe2 plus, you see that the PE value is now much lower, right. So, now as you see that and out there, because of the complex formation, right, you see that iron would tend to reduce, or ferrous iron would try to or tend to reduce your PCE, right, or C2Cl4. But if you consider no complexes, you would have observed that, or if you had no complex formation, you would have observed that it would have been C2HCl3, I guess, right, what do we say, oxidizing Fe2 plus to Fe3 plus. That is what you would have seen earlier, right. So, let us look at what we have earlier. So, if this was the case here, what would you have seen? You would have seen this particular reaction to be swapped, right, which has to be the oxidation reaction. So, C2HCl3 would have then what do we say, reduced Fe3 plus to Fe2 plus, pardon me, I guess I might have misspelled it earlier. So, in this case you would have C2HCl3 is going to reduce Fe3 plus to Fe2 plus, right, and this case as in when there is no complexes being formed, right. So, obviously you now tend to understand or appreciate the relevant aspects. So, if someone did not consider the complexes or did not have the background, they would have had what do we say, an erroneous understanding of the system. But again, keep in mind that we are not yet done, and why is that? Because in the practical scenario or out there in the nature, what else would you expect now? You know that you will also have formation of the solid, right. So, here until now we have looked at, let us say, no other reactions other than redox, right, no other reactions, right, and then we considered complex formation, right, and now we are going to move on to the other case when we are also going to consider the most practical or natural scenario out there, complex formation and solid phase or the precipitation, I guess, right. So, from your background, let us say that ferric iron can precipitate out too, and then let us try to understand how the system would change, or what it is that we need to understand about system when we consider the natural case of the redox, the complex and the solid phase being present, which is what you would what we say expect out there in the nature, I guess, right. So, here I guess as we go through from just the redox what we say example to the redox and complex and to the more natural example or realistic scenario, I guess, right, of redox, complex and precipitation, you will be able to understand better, I guess, right, why you need to have the relevant background in the complex formation and the precipitation and dissolution and so on. So I guess we'll continue this particular aspect in the next session, and I guess with that I'll be done for today, and thank you.